Let's solve a hard A-level question from paper 3 from OCR Physics A. We have a ball coated with conducting paint that has a certain weight, 0.03 newtons, and a radius of 1 centimeter. The ball is suspended from an insulating thread. The distance between the pivot and the center of the ball is 120 centimeters. The ball is placed between two vertical metal plates. The separation between the plates is 8 centimeters. So if we're given the voltage and the separation between the plates, chances are we're going to have to be using the E is equal to V over D equation. So the ball receives a positive charge of 9 nanocoulombs when it's made to touch the positive plate. Okay, so in this case, this plate here will be positive because it's connected to this end, and this plate here will be negative. What's actually happened is that this ball here reached the positive plate, it required a positive charge, then reached this point and is now balanced between the two plates, meaning that it's no longer moving. So the first question showed that the electrical force acting on the charged ball is 4.5 times 10 to the power minus 4 newtons. So for this question, what I'm going to use is simply that F is equal to E multiplied by Q. We know that E is just equal to V over D multiplied by the charge Q. Now the voltage is just equal to 4,000 volts divided by the distance between the plates, which is 8 centimeters, so it's going to be 0.08, multiplied by the charge, which is equal to 9.0 times 10 to the power of minus 9. Putting this into a calculator, we are going to get 4.5 times 10 to the power of minus 4 newtons. Part 2, draw the diagram above, arrows which represent 3 forces acting on the ball. Label each arrow. I'm not going to forget to label them. Okay, now let's have a look at the diagram. We have, first of all, the weight, which is acting vertically downward. So that's W. We're going to have the force of tension, which will be acting along here, and we're also going to have a purely horizontal force, which will be towards the negative plate because the ball is positive, which will be acting along here, and this is our electrical force F. Okay, by taking moments about the pivot or otherwise, show that X is equal to 1.8 centimeters. Now, I personally find the method of this question using moments a little bit confusing, and I think there's a slight inaccuracy in the marks. So let me show you the way I would do it. First of all, I'm going to resolve the tension into two components. So we know that the tension will have a horizontal component, which will be equal to the force, to the electrical force, because it has to be in balance. So I'll just draw this over here. And we'll also have a vertical component, which will be acting upwards. So if this here is the ball, because it's staying in place, the horizontal force will be equal to the electrical force, and the vertical force acting upwards will be balancing out the force due to gravity, the weight. What I'm interested in is this angle theta over here. Find this angle theta over here. I could simply use the inverse tangent because I know what the electrical force is. We've just calculated that, and we know what the weight is because we're given that in the question. So let's do this way. So I'm going to say that theta is equal to tan inverse tan of the opposite, which is the electrical force, divided by the weight, which will be equal to inverse tan of the force, which was 4.5 times 10. What power was it? Let's see, 10 to the power minus 4, divided by the weight, which is given in the question. It is 0.03 newtons. So divided by 0.030 newtons. And let's put this into a calculator. And what we're going to find that the angle is very, very small indeed. It's around 0.859 degrees. So this diagram is definitely not up to scale. Okay, now that we have the angle, we could really easily work out the distance. Remember, these are just forces, they're not actual distances, but we also know that this distance here is 120 centimeters. So suddenly we have this triangle where we know that this thing is 120 centimeters, and we want to know what x is given that we have theta. Well, we could simply use sine of theta, because sine is just equal to opposite over the hypotenuse. Because this is the right angle, this here will be equal to the hypotenuse. So I can just say that sine of theta is going to equal to my opposite, which is just x divided by 120, meaning that x will be equal to sine of theta multiplied by 120, and we'll leave that in centimeters because our final answer needs to be in centimeters, which is going to give us 1.799, which is approximately equal to 1.8 centimeters, up to 2 significant figures. Part B, the ball is still positively charged. The plates are now moved slowly towards each other while still connected to the 4,000 kilovolt power supply. The plates are stopped when the separation is 5 centimeters. Explain the effect this has on the deflection of the ball and why the ball eventually starts to oscillate between the plates. Okay, so first of all, because your distance between the plates is decreasing, this would mean that the electrical force will be increasing because the electrical field is increasing. And I've backed this up using an equation. So the electrical force increases because F is equal to VQ over the distance, D decreases while all the other quantities are constant. Just because they've given us an actual value, I've decided to calculate the force, even though it's not part of the mark scheme. But because they've given us an exact value, 5 centimeters, the force is 7.2 times 10 to the power minus 4 newtons. It also gives me an idea that the ball will probably also be touching the opposite plate. And the horizontal deflection, x will increase because the force has increased. So if you think about it, what's actually happened is that this vector here has increased significantly, and if it's increased significantly, this means that the ball will be deflected more. Now, as the ball is deflected more, it will touch the opposite plate and will acquire the opposite charge. When it does so, it will repel and be moved back into the opposite direction, and this whole cycle will oscillate. So you're going to have the ball which will be oscillating between the 2 plates. Part C, when the ball oscillates between the plates, the current in the external circuit is 3.2 times 10 to the power minus 8 amps. A charge of 9 nanocoulombs move across the gap between the plates each time the ball makes 1 complete oscillation. Calculate the frequency F of the oscillations of the ball. Well, given the current, we know that I is equal to delta Q over delta T. Delta T will be our time period in this case, because every time a charge moves across the gap, this will essentially be 1 time period. So we can say that I over delta Q will be equal to 1 over delta T, and 1 over delta T is actually going to be our frequency. Therefore, the frequency will be equal to I, which is 3.2 times 10 to the power of minus 8. I'm going to be dividing that by 9.0 times 10 to the power of minus 9. Let's see how many hertz that is. So it's going to be 3.2 times 10 to the power of minus 8 times 9.0 times 10 to the power of minus 9. So that's 32 over 9, which is 3.55 recurring, which is 3.6 hertz, up to 2 significant figures. Now, one of the hardest parts in paper 3 is actually starting a question. And if you're struggling with that, you need to have a look at this video over here.